All right. So in this platform, we shall have a continuation from the last part that we had. Remember, we managed to talk about the speed control, the calculations that you might be given. So this is another typical question that we have that you are going to consider. So the procedures, remember, always you must read the question carefully. Then you must draw the diagram that is representing the information that you're given, so that now you'll be able now to use the formula that you are going to use, which is the main speed control formula to calculate whatever that you're given. So let us see, how exactly are you going to know? This is a speed control type of a question. You are given here a 300-volt shunt motor runs at 1000 revs per minute while drawing current of 50 amps from the supply. So this motor is drawing a current of 50 amps from the supply. The armature and shunt field resistances, we are given the resistances respectively. Then the speed motor is increased. This part here is the one that is controlling our question. We know that this is no longer just a normal question that we are used to. It's no longer just a shunt motor that we calculate those normal calculations. The speed of the motor is increased by connecting what was connected, a 100 ohm resistor in series to the shunt field. In our previous case, we had a condition where a resistor was connected in series to the armature. But in this case, it is to the shunt field. Remember, this is a shunt motor. The connection of this resistor changes a lot of things. It changes a lot of things. I talked about the change of the load current, the change of the armature current. A lot of things will be affected. The generated EMF on its own, the speed of the motor, the torque of the motor, all those things will be affected. So you know that this is a speed control problem. So there we are asked to calculate the new speed of the motor if the load torque is reduced. All right, so we're going to talk about that. But as you can see, that's a speed control question. So according to the information that we have, let us just consider this so that we just answer this question. We are given is a 300-volt shunt motor. Then the diagram that you're going to have, remember your shunt motor, guys, we're going to have something of this nature. I talked about this with the load current taken from the supply. Remember, it's a motor, it takes in current, and another one to the field, another one to the armature. So since this is the original diagram, this we are going to refer as the load current one, the field current one, the armature current one. All right. We are given everything in this case, all right? The 300-volt, the speed, which is 1000, which is at full load. The speed will be 1000 at full load. Then we are given the current there of 50 amps taken from the supply, which is your load current. Then the armature and shunt field resistance is being 0.15 for the armature, and for the shunt field, 150. So the shunt field, which is this one, is the 150. So we're just going to call this RF1. Then we have got the armature. All right. So this is RA for the armature. That is what you are having from the original conditions that you're given. Then a certain consider is given now that the speed of the motor is increased. It is increased by what? By connecting a 100 resistor in series to the shunt. Make sure you understand that part, because another part, they're going to connect this to the armature part, to the armature circuit. In this case, it was connected in series to the shunt. Remember, this is the shunt part of your circuit. This one, sorry for that. This one. then your armature circuit. So it was connected in series, meaning to say from the original, we are going to have the final circuit here with a resistor connected in series to the what? To the shunt. If it was connected to the armature, you're going to connect here. But this one is to the shunt. So it is going to affect a lot of just connecting this resistor. It affects a lot of things. The load current of the final circuit is going to be affected. The armature current on its own, the field, a lot of things that we're going to have will be affected. All right, no problem. Let's continue because we talked about this. So the question was, calculate the new speed of the motor. We need the new speed, meaning to say of the final part. What is going to be the new speed? Remember, originally we are given the speed as 1,000 revolutions per minute. But the final speed, we do not know. Okay, let us continue. This speed is supposed to be calculated if the load torque is reduced by to 80%. Take note there. It is reduced to 80% of the full load value. The full load value is of the original condition. At original condition, you'll be having T1. So T2 of the final condition, it is reduced to 80% of, guys, whenever you're given of, it's a product, like 80% times. So it is 80% of the load, which is the full load value. The full load value is your T1, which is of the original condition. That's where we have the full load. So it's 80% of T1. Take note. They can say it is reduced by 30%, reduced by 30% of the full load. Take note, this is different to this. This one, it is reduced to, that is, it is given to that value. It is now to this value. But reducing by means you are removing, it's like you increased a certain price by 30%. By 30%. You reduce a certain price by 30%. So it means you are subtracting the 30% if it was like that. But this one is reduced to, it's to that value exactly. You are not subtracting anything. So be careful on that one. Okay? When it is maybe reduced by 30%, so meaning to say you're going to subtract that 30% from what? From the 100%, it is now at 70% of T1. But in this case, they are saying it is reduced to 2. So that is where I'm saying read the question carefully. It seems as if you are wasting time, but this part, if you don't understand it, everything will be affected. So this relationship as a decimal, 80%, remember, is same as 0.8 if you divide by 100. So this is the relationship that we are seeing here. That's T2 is equal to 0.8 of T1. All right. So that is a condition to be used relating the two, which is the torque and the torque of the original and that of the final circuit. Not forgetting that always this condition is going to be affecting flux being proportional to the what? To the field current, which will affect our formulas. All right, so this is what you're going to have. You draw your diagrams, you put in your values. Remember, this is the extended resistor that we connected in series. You can even write it as Rx is equal to, you can even write it as R additional, whatever that you want. You can just leave it like that. Then this is the field result, which is the same, does not change. armature current is not even affected. So we need to calculate this speed N2. And from our formula sheet, this is what we have. Remember, I talked about these formulas where the speed is considered. So knowing that the flux is proportional to the field current, we can write this formula that we are seeing from the formula sheet in this way. Like I explained before, you can just rewrite this formula as E1 over E2 is equal to, then you've got the speed, then there you're going to use the field current 1, N2, then you consider the field current 2, since flux is proportional to the field current. Since flux is proportional, directly proportional, you can substitute where there was the flux with the field current, because that field current can be calculated according to the diagrams that we have. Remember from your Electrotechnics N4, a shunt motor. If you're working with a shunt motor, this field current is your shunt current. That is the shunt field. So the question is, you want to calculate what? N2. Circle that part that you want to calculate, okay? You need to calculate N2, which is the speed on the final. Then what are we having? We have got N1, the speed. With this one, we have it. We do not have the field current 1. Never calculated this. We do not have field current 2. We do not have E1. We do not have E2. So we need to calculate these. We need to calculate this. Whatever that you can calculate, write it aside, calculate, write it aside. That is how you answer these questions. As simple like that. You just need to work with more questions. Work with more questions. All right, so let us see what is easier from the original circuit. What is it that we can calculate from the original circuit? We can calculate the field current, the generated EMF, all these we can calculate. All right, so let us start with the field current. So the field current 1, like I say, the field current is same as this is your shunt, the shunt current, all right? Remember from your N4, we are just referring like just the shunt. That's the same thing. From the supply voltage over the R field, which is our R shunt in this case, that is the shunt resistor, we can calculate this. There's only a single resistor that we are given there. So that is enough. So 300 divided to 150, that is going to give us 2 amps. So, all right, so this one is direct. In the same manner, we can also calculate this part of the circuit, because there is a resistor and also the resistor of the field. We can calculate also, this field current too. All right, let us just finish up with the field currents. So on the second part, which is our final circuit, we are going to use V over the field. It is now affected. Previously, if you check our previous question, we were not having any effect along the field. So on that condition, I even said you can consider your formula to say the field current and the field current were the same. You can cancel and you end up with this over this is equal to this over this. But in this case, it is being affected because there is a resistor connected in series. So we are going to add that resistor. So let's say this is your Rx, maybe you want to call it R additional, whatever way that you want. So you can just write this formula as Rx plus Rf2. All right. So the Rf2 is just to say the final circuit. 1 is denoting the original circuit. 2 denoting the final circuit. Wherever we consider the final circuit, we just write 2. So do not worry, even if the values are the same. This is just to denote that we are dealing with the final circuit. All right, the V we have, which is 300 everything over Rx, so which is the given resistor in series. Remember, in series, you add from your N3 electrotechnology there, we talked about these things, even from your science, remember, on those electrical circuits, you understand how to calculate the current. So anyways, let us consider this. If you were to divide properly, this was going to give you 1.2 amps. So I also want you to confirm on this part. So that is 1.2 amps. As you can see, it's different because there is a resistor which is connected in series, so it affects everything. All right. The field currents are there. That is, we calculated. All right. So you see now I ended up not changing up, not removing what I wrote there. Sorry for this, guys. So we calculated these ones. We saw that they're different. Field current 1, the field current 2. So let's think of the generated EMF 1, the generated EMF here. From the original circuit, this original circuit, we are considering this as a motor. So do not worry about the formulas. If you've forgotten, your formula sheet is there. From the specific EMF equation, we can consider, remember a motor, it has got the back EMF. So we're going to consider a negative there. So E, which is E is equal to V minus the armature current times the resistance of the armature circuit. So this is, we're just gonna consider E1, V1. This is a 1, just to consider to say of the first circuit. Don't worry about that. So in this case, are we having these from the formula, from the diagram? V1, which is the supply, we have got the supply. The armature current, we do not have the armature current. So you're supposed to calculate this. Then this is representing the resistance of the armature circuit, everything of the armature circuit, everything of the armature circuit. So the part of the armature, we just have the armature resistance. There's nothing in series or what. We just take this as it is. If there was a series resistor in the armature circuit, you add that one. It's part of the armature. So that is your specific EMF equation. All right, so let us calculate the armature current. We can calculate this because remember, we have got the field current 1. We calculated this. The field current 1 is 2 amps. So this is 2 amps from your Kirchhoff's law. Current entering is equal to the current leaving the circuit, which is the load current 1 is equal to the field current 1 plus the armature current 1. So we can calculate the armature current 1 because we have got the field current. We can make it the subject. It's up to you. The load current 1 minus the field current 1 is equal to the armature current, where the load current is 50 minus the field current 2 amps. This will give us the armature current. So that is it, which is going to be 48 amps. So with the armature current, we can calculate the generated EMF, which is V is 300 minus the armature current of the first circuit, which is 48 amps times everything that is of the armature circuit. But as you can see, there's only a single resistor, which is our armature resistance of 0.15. So that is it. So if you were to subtract here, you're going to obtain 292,8. That's 292,8 volts. So this is our E1. We just have to calculate everything, guys, that is needed on this formula. Everything. So E1, we have this one. Let's think, sorry, that is E1. Let's think of E2, which is the generated EMF of this part of the second circuit, the final circuit. If we were to calculate the generated EMF, you're going to think of this. I actually talked about this because it's the same thing. V2 minus, we're going to have the armature current 2, then the resistance of the armature circuit. The problem of this formula where we are going to be limited is on the armature current. Because we actually do know that from this part that we had, remember, we calculated the armature current because we were given, we have got the load current, we have got the field current also. What we do not have is the armature current. That is the only thing that we do not have, this armature current. But if we are to take it on the original, on the final circuit, we do not have the load current. So it is now we do not have the load current. The field current too, we have this one. We calculated the field current too. Remember, we got 1,2. We have got the field current too. The armature current too is the one that we are supposed to calculate. So at the end, you see that we do not have the load current too. We do not have the armature current too. We do not have two things from a single equation, from just a single equation. There are two unknown. So it was going to limit us to calculate the armature current too. That is where we have to opt for another formula. So this doesn't mean that this formula does not work. No, it does work. But we are limited just for the to calculate armature current. All right, so let me not remove this. So, okay, just gonna leave this one. What is affecting, I'm saying the formula of, I want you to be careful, guys. The formula of the load current 2, because it was gonna be load current 2, is equal to field current 2 plus the armature current. This is the formula that I'm saying it is not going to work because we do not have the load current and armature current at the same time. So we have to opt for another formula to find the armature current because everything is there. V2 and this resistance of the armature, they're available. We have these ones. Only the part of what? Only the part of armature current is not there. So how are we going to how are we going to calculate this? We refer back to the torque now, this one. The relationship between torque is that it can be used to calculate currents also. It can be used to calculate currents. Let's go back to our formula sheet and see. Let's go back to our formula sheet. I want you to see it here. Where the torque is, we can see also the current is. So we can use it to calculate the armature current. This is the constant, guys. This cancels this constant here. And remembering that the flux and this flux here will be replaced with armature, with the field current, because we said the flux is proportional to the what? To the field current. So that was going to help us to calculate the armature current because we are limited from the previous formula that you used before. So you might wonder, why is it that I'm using this formula, but next time it's impossible? It's because you do not have some of the values along them, along what you're given. So this is our formula T1 over T2. Remember, it is equal to K. Then we have got flux 1, the flux, which is the field current now, proportional to the field current. Then we have got the armature current 1. Then we've got the field current 2 and armature current 2. This time, these field currents are different. They're not the same. So you cannot cancel, so this and this are the same. No, they're different. 2 amps, 1,2. They're different. So we are just going to substitute what we are given. So I talked about the relationship between T1 and T2. So this one is not a problem. T1, I said you just write as it is. But T2, you write it in terms of T1 so that it will cancel. So T1, you just write it as it is. But remember that you're given that T2 is equal to what? 0,8 of T1 from that percentage reduction that you're given. So that is 0,8 of T1, which is equal to the field current 1. You calculated the field current 1, which is 2 times the armature current 1 is available. Remember, you calculated this armature current 1 on this circuit, which is 48 amps. So we have this one, that is 48, everything over the field current 2. which is 1,2 times the armature current 2, which is the one that you're supposed to calculate. Remember, you need the armature current 2 here. So T1, remember I said it cancels. This is 1. So we're just going to cross multiply. 1 times 1,2 times armature current is 1,2 times armature current 2. Then here you're going to multiply 0,8 to 2 times 48. So that will be times 0,8. Definitely you will divide by 1,2. Whatever that you are going to obtain here, you're going to divide it by 1,2. So this was going to give us the armature current of the second, which is the final circuit. And that was 64 amps. The purpose of this armature current is because we need this one to obtain. We need this value in order for us to calculate the generated EMF. So now we can substitute everything. Remember what you are considering. It's of the final circuit, the final consideration, the final condition. So E2, the generated EMF was going to be V2, which is the V 300 minus the armature current, which is the one that we just calculated, that is 64 times everything which is part of the armature circuit. The part of the armature circuit, this time there's only that armature resistance of 0,15. We do not have anything in series or like what we had in the previous case where a resistor was connected in series, where you have to add that one. There is just that armature resistance. So you have to be careful on your calculations or how you present your formulas. Understand your formula, what it means. So that's our E2 was going to be 290,4 volts. So that is the generated EMF. Okay, so everything now is there. Everything. I think you can consider this E2 is there. So that is it. Remember, you want to calculate N2. We have everything. We can even make N2 the subject. If we cross multiply here, that is going to be E2 times N2. Field current 2 is equal to, there we're going to have N1 cross multiply to this. So that's N1 field current 1 times E2. Remember what you want as this N2. So you divide by E1. So you're going to divide by E1 field current 2. All right, do the same thing here, E1 field current 2. So that's it. That's it here. We've got our N2. So N2, which is the speed of the final, is going to be given by this formula here. So this is the formula that you're going to use. So it's just a matter of substituting. Remember, to use this formula is because you calculated everything. You are now sure that everything is there. All right, so let's substitute N1, the speed of the original, that is 1,000 rests per minute times the field current 1, which is, we calculated this one, remember here's 2 amps. So that is 2 amps times E2, which is the generated EMF of the second, which is the original, which is the final. And also E1, we calculated this one, the side, if you still remember here, E1, 292,8. So that's 292,8. And the field current 2, we also have this one. We calculated this. Field current 2, remember, this is 1,2 amps. So that's 1,2. So this is how you're going to calculate these questions. The speed in revolutions per minute was going to be 1,653,005. So that's in revolutions per minute. So speed controls calculation or speed control calculations, the more you attempt your questions, the more you actually understand this, like the conditions that you're given. They are going to just give you a different conditions. So read the statement that you're given here properly. Understand that the statement that you're given here. It is the one that matters. The information that you're given here. With the information, draw clear diagrams that you're going to use in the presentation of that information that you have. Present it on a diagram. Then the formula for the speed control, which is our main speed control formula. Remember, we had a flux there, but I said flux is proportional to the field current. So we shall have more questions of this typical nature so that you do understand how they ask this, how they do ask these questions, and how are we going to answer these typical questions. So make sure that you work through your question papers. Where there are questions, we can work on those questions along this platform, which can help us now in our revisions. So at least on areas that we have covered so far, if there are questions, we can work on those questions. Still yet to cover other areas. So while after that, we bring questions on those areas. If you cover the AC, let us bring questions on AC. If we cover transformers, let's bring questions on transformers. So for now, this part of the DC machines, if there are questions, let us know about those questions so that we can assist each other along on what you have already covered or studied from this platform. Yeah, let us bring questions. I don't mind. Let us bring questions.